Powerful collaborations, cutting-edge science, and curious minds coming together for a glimpse of the future. Stay tuned as we look at the latest updates on some of the most promising technology projects. Welcome to the EUVATION podcast. I'm Peter Ballant from Technicon. Today, we once again look at the IPC project. IPC stands for Individualized Pediatric Cure. This is a huge EU-funded effort to assist doctors in finding the most effective treatment for children with tumors. There is no one-size-fits-all approach, and doctors, clinicians, oncologists, biomedical engineers, and computer scientists are working together in IPC to use data, human samples, and artificial intelligence to tailor treatments for kids while minimizing the risks. It's no easy task, but IPC is making inroads in this area. Today we speak with Matteo Manica from project partner IBM. He's a research staff member at the IBM Research Lab in Europe at the Zurich location. In the wake of the COVID-19 restrictions, we speak with Matteo remotely from his home office in Zurich. Welcome to the show, and tell us about IPC and your specific role in the project.
IPC is a European project about the development of a precise and precision medicine solution for pediatric tumors. The main motivation behind this project is that these type of tumors are quite rare, but when they happen, usually we don't have effective or efficient treatments to handle this type of tumors. We obviously focus on curing the disease and ensuring the survival of the patient, but a lot of the treatment options that we have might have extremely negative side effects on the long term. So we might put the patient through a life and long-term serious health consequences. So the main reason behind working on these specific tumors in IPC is to try to optimize and find better therapies that might work as well as current therapies are doing, but the idea is that we might try to tailor them on the specific patient in order to have a better outcome intended as less consequences in the long term for the patient.
Okay, so this really sounds like this is about personalized healthcare or precision medicine. Is that correct?
Exactly. This is basically the core concept and the core idea behind this project. Basically, the possibility of integrating different data types, molecular data, also data from publications, data from databases, and also molecular data at different levels, from the gene expression to the proteomic expression, so to the protein expression, with the intuition that if we can put together and pull together these different data modalities, we can try to basically understand better the disease of the specific patient or a specific subpopulation of patient and find better therapeutic indications.
So IPC is a project that addresses perhaps treatments of children in the future. And if we look at what's happening right now, what are the effects of not having something like IPC?
Yes, that's a very interesting question. I think the effects are really the fact that, and don't get me wrong, this is the best possible treatment we can probably give and the best possible therapeutic options, and they really save a lot of lives already. But the main issue with some of these treatments is that first, in some cases, this doesn't work because patients and kids respond differently to different therapies. So the same therapy applied to two different patients can really have a different outcome based on the specific tumor that the patient is developing. And the second aspect is also the fact that we usually manage to cure the patients with current therapies, but these therapies might be really toxic in the long term. So the idea of taking a personalized medicine approach is that we can basically try to minimize this toxicity of the treatment, these negative longer term conditions, and also improve the current existing therapies. Obviously, this is a very bold goal, but we really think that by taking this holistic approach, and equipping ourselves with the weapon of personalized medicine and multimodal data analysis, we can try to basically reduce this delta between what we can actually have and what we have right now, and what will be the best treatment option that is completely side effects free and basically with a super low margin of failure.
Okay. And if you look forward a few years down the road, and if you're looking at the project ending and looking back at some of your successes, what would you consider a success for IPC, or what does success look like?
Yes, that's very also interesting, and I think that here it's really important to set the right expectations, but not being too conservative when doing this. In the sense that I think it's in pediatric tumors and tumors in general are a problem that are far from being solved in the next 4 to 5 years, in the next decade, I would say. So what we can realistically do, and that can really help, is to basically develop a framework using all the expertise coming from the different partners, where we can basically share tools that can help practitioners with the current data that are available to take more informed decision about a therapy or about the potential outcome for a patient. And what I think would be really successful is to make this platform broadly available. So having a single place where we combine different techniques ranging from mechanistic model to AI to also intensive HPC application, that medical practitioners or researchers can just access and run analysis and perform predictions with their own data. In my opinion, this would be an incredibly useful resource. And if we combine this also with the data banks that some of the partners are already making available and are maintaining, we can really have a big impact in this field.
So you say the samples are rare, which makes me wonder, do you have access to samples from around the world, or is your project strictly focused in looking at samples from Europe?
The project actually is not looking only at samples from Europe. We have the luck to be collaborating with the partners spread almost all over the globe. Especially we have a collaboration with Kids First initiative, where they basically have a data bank of multiple pediatric tumors coming from US and Europe, and they do an aggregation of this data. The nice thing of this aspect is that we can really pull together information from different locations, so we don't have any specific bias on the type of disease that is developed in different communities. The collaboration is really interesting because we are putting together partners not only from Europe, but also from US, from Australia, and we can really rely on an incredible platform to share data and collect this data and analyze them to basically gain actionable insights on the different disease types.
So it seems like the real muscle in this project is actually in the data.
Yes, exactly. This is what I would say is really the fuel. If we have to do a parallelism, the data is what you absolutely need to get the whole machinery going, and all the activities of the modeling groups like the IBM Research Europe one or the other groups from more computational biology applied research are basically making sure that the engine and all the different elements of this machine are perfectly tuned and work in a synergistic fashion. So, as I always like to think about it, basically the data providers are really giving us the fuel to make our algorithms run predictions, and our job for all the computational group members, but especially I can speak for IBM Research, is really to make the best out of this fuel. So to develop good and robust methods that can integrate different data types and can get the best out of this gold mine of patient information.
Okay, and I want to back up a second. You mentioned AI, which is artificial intelligence.
Yes.
What kind of role does artificial intelligence have in this project IPC?
Yes, so what we are mostly doing, and we are one of the main partners working in artificial intelligence application to pediatric tumors in the context of IPC. is that we are basically trying to tailor state-of-the-art methodologies from machine learning, deep learning, and artificial intelligence in general to basically create models that can help us in different aspects. First of all, understanding better patient subpopulations, so finding patients with similar similar tumors in order to understand whether we can try to treat these patients in the same way, or even using these algorithms to find the differences between patients and understand why something worked on someone and something didn't work on someone else. And these techniques are very useful in this case because they basically can be developed without any input bias from the person that is actually creating the model. So we are basically somehow suspending our judgment when we use this type of models, and we can try to use all the insights coming directly from the data. So having these tools at our hand and using them can really help us to learn something completely new for these diseases, and that can give us this delta in terms of novelty to improve or give different recommendations on current therapeutic indications.
Okay, and since we're on the topic of artificial intelligence, maybe now is a good time to debunk some of these popular myths about AI in the medical fields. Things like in the future, computers will make decisions about your healthcare, not necessarily doctors, or computers will replace doctors completely. What do you have to say about these notions?
Yeah, this is a very interesting debate in the scientific community about the role of artificial intelligence, especially in healthcare applications or in these, let's say, performance critical sensitive applications where we are really putting the life of humans in the first row and at risk. So the first thing, and this is a personal take, but also the opinion of many experts in the sector, that we have to keep in mind is that artificial intelligence applications and in general these models purely based on data will never probably take any decision without any doctor supervising this or approving. So I want to assure the audience that this probably will never happen, and I would say luckily. The role for this type of tools is probably really to make the life of the doctors easier and make them more efficient. A good example that we can think of is the work of pathologists when they have to look at these histopathology images to, for example, grade a specific cancer. And this operation is really important and fundamental to understand very well which type of cancer we are looking at and how to treat the patient and which therapeutic options to take, for example, surgery or not surgery, chemotherapy or not. So this is a very important task that is super time consuming for the pathologist itself. And AI can really help to speed up this process by basically recommending area of interest to the pathologist or basically selecting regions of the biopsy to look at. So there are so many ways that these tools, and this was just an example, can really speed up the daily routine of a doctor. And I think that this is the exact role that we want for this type of tools.
So for the people who are still nervous about artificial intelligence in medicine, we could tell them, this is just giving your doctor more information to make a better decision about you.
Yes, I completely agree with this statement. The idea is that all this ecosystem of tools, models, and techniques will never be used as a replacement for a doctor and will be only used to basically help the doctors to be more efficient. This is probably the way they can be best used, and they can help to obtain tangible results in the short term. But I want to really tell you that most of these models are really dummy workers that are very good at doing a single thing. They do it very well, and this is why they can outperform humans in specific tasks. But connecting all the dots and taking these results and using them in a constructive fashion is something that only an expert and a doctor can do in the best possible way. So maybe we should just add a disclaimer when we use the noun phrase artificial intelligence in medicine.
Well, yeah, that makes sense. And I'm glad that you pointed that out because I think many people tend to look at artificial intelligence in one way and never really consider how it could be used in many different ways. You're also working on a closely related endeavor called PACMAN. Now, how does PACMAN support IPC?
The PACMAN project is a project about designing anti-cancer compounds using deep learning techniques, and it started just before IPC. In the context of pediatric cancers, what we are doing with PACMAN is that we are basically using our model that is tailored to propose novel potential effective candidates to treat a specific tumor, looking at the gene expression profile of a specific patient. And in the IPC project, what we do is that we basically use this tool to generate drugs for the specific cancer types we are studying in IPC, and basically doing this in also a profile-specific fashion. And what I mean by that basically if we have the sample gene expression from patient X, we can start to propose drugs that are extremely effective to cure the disease of patient X. Obviously, this is a bit a jump in the future. It's not feasible yet to have a specific drug for a specific patient. And also, if you think about it, obtaining approval for a patient-specific drug is quite tough, let's put it in this way. But here the point is really the fact that we can basically check what would work best for this patient in terms of modeling, and we can then use this hypothesis to try to generate novel drugs that could treat specific subpopulation of patients in an effective way. So the role of PACMAN in IPC is really to basically leverage different data information and try to come up with new candidate therapeutic agents that can help us to shape new medicines in the future to treat pediatric tumors.
Perfect. And IPC focuses on pediatric cancer. What's the reason for that? Why not look at something that's more prevalent, that's not so rare?
The main reason is that while the numbers are not in favor of the cause, let's put it in this way, it's quite a pressing problem because pediatric tumors are quite rare, but are also quite lethal. So I think it's very important to improve therapies there. And as we also mentioned earlier, I think that once we are able to cure these patients, in a lot of cases, we basically have a therapy that leaves this long-term damage in the patient that survived the tumor. So while the numbers are quite low, I think it's very important that we ensure that we have effective treatments for pediatric tumors, because they can really change the quality of the life of an enormous number of families. Because if you think about it, having to take care of a child with a specific condition that then is protracted a long time is really impacting the life of all the people around the child. And I think that IPC in this sense can really be a game changer if all the premises that we put down are then satisfied.
Okay, so it sounds like many times with the treatment in these pediatric cases, this involves something that could lead to other lifelong problems, which are side effects of the treatment.
Exactly.
Okay, and that's what you want to prevent. And I think that, that's the honorable goal of IPC. So thank you very much for your efforts in this project, and we wish you and all of your project partners much success in the completion of IPC.
Thanks a lot. I would be happy to join again the podcast to comment on some results as soon as we have something interesting to share.
Yeah, that's great. And I'll sort of stay in touch. And if we have the opportunity to sit down again and talk about some new results, I'm happy to do it. So thank you for that.
You're welcome.
For more information about IPC, go to their webpage at ipc-project.eu. The IPC project has received funding from the European Union's Horizon 2020 Research and Innovation Program under Grant Agreement number 826121.